This is section 7.3 and 7.4, similar polygons and similar triangles. We know what it means for two polygons to be congruent. Congruent means they have the same shape and the same size. But what if we had polygons which were the same shape but not necessarily the same size? Take these two pentagons here. They are the same shape, and if we measured all the angles, we would see all the angles are the same measure, but they're clearly not the same size. We know that because PQ is 20 and VW is 32. They're clearly not the same size. So what do we call these shapes then? We call these polygons similar. The definition of similar polygons is that two polygons are similar if their vertices can be paired so that corresponding angles are congruent and corresponding sides are in proportion. It means their lengths have the same ratio. So that all of the angles have to be congruent and their sides need to be in proportion. So these two polygons we had above, which I've redrawn here, they are similar if we know that all the angles are congruent. So if we know that angle P is congruent to angle V, and angle T is congruent to angle Z, and angle S is congruent to angle Y, and angle R is congruent to angle X, angle Q is congruent to angle W, and we know that all pairs of corresponding sides have the same ratio. So we write, if they are similar, we write P, T, S, R, Q, and the symbol for similar is this squiggle. And then we list the vertices of the other pentagon in their corresponding order with the first one. So V corresponds with P, and we go around in the same direction that we did on the first one. V, Z, Y, X, W. So this means similar. So if they are similar, what do we know? Well, from part 1 of the definition, we know that corresponding angles are congruent. So which angles correspond with each other? That means angle P is congruent to angle V, angle T is congruent to angle Z, angle S is congruent to angle Y, angle R is congruent to angle X, and angle Q is congruent to angle W. The corresponding angles are congruent. From part 2 of the definition, we know that the corresponding sides are in proportion. It means the corresponding sides have the same ratio of lengths. So 20 over 32, which is P over Q, which is PQ, over VW, has to be the same as the ratio of all the other corresponding sides. So PT would correspond with VZ. So if I divide those, I need to get the same ratio as I did with PQ and VW. Same with TS over ZY, SR over YX, and RQ over XW. So what is that ratio? Well, it's 20 over 32, but we can simplify that. 20 over 32 is the same as 10 over 16, which is the same as 5 over 8. So if I take any pair of corresponding sides to these similar polygons, and I divide their lengths, I will always get 5 over 8 for these two polygons. So the sides are not congruent, they're not the same length, but the ratio of the sides is always the same, it's constant. And in this case, that's 5 over 8. So if two polygons are similar, then the ratio of the lengths of two corresponding sides is called the scale factor of the similarity. In the example above, that scale factor is the two sides we know, PQ over VW, which is 5 over 8, as we calculated. That's called the scale factor. Here's an example of two similar polygons. We're told that quadrilateral ABCD is similar to quadrilateral A prime, B prime, C prime, D prime. That's what they tell us right here. These little apostrophe things above the letters, that means the word prime. And that's just a way of denoting that this point of the right-hand polygon corresponds with point A over here. So we'll call it A prime to show that, emphasize that it corresponds with point A. It's just notation. We could just as easily call them WXYZ. It doesn't matter. But by calling them A prime, B prime, C prime, and D prime, we are emphasizing that they correspond with points A, B, C, and D. Okay, it's just notation. So we know these two polygons are similar. We want to find their scale factor, the values of x, y, and z, the perimeters of the two quadrilaterals, and then the ratios of the perimeters. So first, how do we find the scale factor? Well, we need to take a pair of corresponding sides for which we know both lengths. The only corresponding sides that we know both lengths for are this 20 and 30 here. All the other pairs we have a variable, so that's not going to give us the scale factor. So to find the scale factor, we're going to use dc over d prime c prime, which is 20 over 30, and we should always reduce it if we can, so that's 2/3. Okay? A ratio of 2 to 3. Scale factor of 2 to 3, a ratio of 2 to 3 for the sides. Using that, we can find the values of x, y, and z. So, for example, x corresponds with the 21 over here. So we're going to set up a proportion in order to solve for x. We're going to say x over 21 equals 2 over 3. I need to make sure that I write it in the right order. X is for the left polygon, so the 2 needs to go on the top because it corresponds with the left polygon. So x over 21 equals 2 over 3. So this is the left quadrilateral. They both go on the top. And then I have drawn it, the two numbers corresponding with sides of the right quadrilateral went on the bottom. So they need to be at the same level if they are part of the same quadrilateral. So x over 21 equals 2 over 3. How do we solve that proportion? Well, if you remember, the way we solve a proportion is cross multiply. So 3x equals 2 times 21, which is 42. And we just solve for x. And x equals 42 divided by 3, which is 14. So we're going to do the same thing to solve for y and z. We use the same scale factor, 2 to 3, and we're going to set up similar proportions. But this time y is part of the right quadrilateral. So we have to do 8 over y equals 2 over 3, so that the same quadrilaterals are on the same level. Cross multiply, we get 24 equals 2y, which means y equals 22. And then we need to solve for z. We'll do it the same way. Z corresponds with that 10. Again, z is on the right quadrilateral, so it's going to go on the bottom. The 10 is going to go on the top. Equals 2 over 3. So 30 equals 2z, which means z equals 15. So ratios and proportions play a huge role in similar polygons. Okay, part C, we need to find the perimeters of the two quadrilaterals. Well, now that we know x, y, and z, that's easy. X is 14, y is 22, and z is 15. Okay, so the perimeter of the left polygon, the left quadrilateral, A, B, C, D, so the perimeter of A, B, C, D equals Perimeter is adding up all the sides, so 8, 20, 10, and 14. 8 plus 20 plus 10 plus 14. We add those up, we get 52. And the perimeter of the other quadrilateral, A prime, B prime, C prime, D prime, we add up all the sides, and those are 21, 22, 30, and 15. 21 plus 22 plus 30 plus 15. We add up 21, 22, 30, and 15. And we get 88. I made a mistake. So when I found y, 8 times 3 is not 44. That's 24. I hope you were yelling at me and about ready to call the geometry police, because that's a big boo-boo. So y is 12 instead of 22. So let me fix that, because that's going to affect this, which makes it 78 instead of 88. And that's important for the point I'm going to illustrate. So I'm sorry about that. Even me, even I make mistakes. Alright, part D, find the ratio of the perimeters. So 52 over 78. And if we simplify that fraction, what do we get? 2 over 3, which happens to be the same as the scale factor. Is that a coincidence? No. The ratio of the perimeters will be the same as the ratio of the sides for two similar polygons. The ratio of the perimeters of two similar polygons will be the same as the ratio of the sides. Alright, now we're going to focus on similar triangles. Triangles are polygons. Remember, polygons are just any multi-sided shape. So triangles are polygons, but we're going to focus on similar triangles. They're the simplest kind of similar shapes we can look at. So we could always use the definition of similar polygons to prove that two triangles are similar. We could show that all three pairs of angles are congruent and all three pairs of sides have the same ratio. It turns out there are simpler methods to show that two triangles are similar. Instead of showing that all three pairs of angles are congruent and all three pairs of sides have the same ratio, it turns out all we need to show is that two pairs of angles are congruent. And that is enough to guarantee us that the two triangles are similar. And we call that the Aaa Similarity Postulate, or angle-angle similarity postulate. If two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. It's easy to see that the third pair of angles must also be congruent, because we know all three angles add up to 180, so if two pairs of them are congruent, that last pair that makes the 180 in both triangles must also be congruent. So that's why we don't need to say angle-angle-angle similarity postulate, because all we need is two angles, and then we're guaranteed the third angles are congruent. So if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. So here we would say triangle ABC is similar to triangle A prime, B prime, C prime, because angle A is congruent to angle A prime and angle B B is congruent angle B prime. Just knowing those two pairs of angles guarantees me that those triangles are similar. This only works for triangles, not for other polygons. Here are some examples. Tell whether the two triangles are similar or not. If they are, we're going to identify what that similarity is. So in number 1, we've got triangle HOK, triangle FOG, or FGO. Are those two triangles similar? Well, they both have a right angle. Angle H is congruent to angle F. Let me make note of that. Do they have any other angles congruent? Well, don't forget about this pair of vertical angles right there. So, angle HOK is congruent to angle FOG. So they actually have two pairs of congruent angles. That means, yes, triangle HOK is similar to, and let me make sure I label them in the right order, triangle FOG. HOK, FOG. Because I have two pairs of angles congruent. Number 2, are these two triangles similar? I know NM is 6, YK is 12. They have a ratio of 6 over 12, which is 1/2. And NO is 8, and YE is 18. They don't even have the same ratio. Plus, we don't know that two pairs of angles are congruent. Definitely no. Not similar. Number 3, do I even have two triangles here? Yes, I do. I'm glad you asked. I got triangle CEJ, but I've also got triangle HCS. Are those similar? Well, they share angle C. They both have angle C, and angle C is congruent to itself by the reflexive property. So angle C is congruent to angle C. That's one pair of angles. Do we have another pair of angles? Well, we know that EJ is parallel to HS. If those things are parallel, then we've got corresponding angles right there. We actually have another pair of corresponding angles on this side, J and S, but all we need is one pair. So angle CEJ is congruent to angle CHS. That gives me two pairs of angles, which means these two triangles are similar. So yes, triangle CEJ is similar to triangle CHS. Keep that in mind when you do your immediate practice problems, and make sure you draw the pictures, or you will not get full points. Number 1, quadrilateral ABCD is similar to quadrilateral A prime, B prime, C prime, D prime. Find A, their scale factor, so the ratio of their sides, and B, the value of x by using a proportion like I did earlier. And number 2, are the two triangles similar? If so, identify the similarity. Say what triangle is similar to what triangle. Or if they're not similar, write no. And that is the end of section 7.3 and 7.4.